Hi everybody, it's Mr. Oliver again. This is going to be the solution for AP Physics 1, Unit 5 Review Practice, free response question number 1. So let's go ahead and get started. Alright, so for this question, we've got a rotating disc that is spinning counterclockwise as shown, and there's two ladybugs standing on top of the disc, assuming that the friction in the bearings of the axle is negligible. Would probably also assume air resistance is negligible. All right, question number A says, is the angular speed of ladybug A greater than, less than, or the same as angular speed of ladybug B? All right, so for any kind of a circular, solid platform, disc, whatever you want to call it, if you've got that circular platform and there is a center axis, then as this thing is rotating around, you can bank on the fact that any singular point on this rotating disc, doesn't matter where it is, they'll all be rotating with the same angular speed as the whole thing. And the reason why that is because an angular speed doesn't care about a distance that it travels, it only cares about the angle at which it's rotating. And so any point on that disk, regardless of how far away it is, will always traverse the same angle in time as any other. So the way you need to think about this is that angular speed is a change in the angle over time, not a change in distance over time, because they all will go through the same angle. They'll all have the same angular speed. So the question A is the same. Right? And that's just a statement of fact. You could just state all objects on a rigid rotating body have the same angular speed. That's all you need to say for justifying your answer. Question II, is the linear speed of ladybug A greater than, less than, or the same? Well, in this case, ladybug A is further away than ladybug B. And so if I looked at it like this, let's say that here's ladybug A right here, and then here's ladybug B, which is a little bit closer. Because ladybug A is at a further distance away than ladybug B, you could conclude that, yeah, ladybug A is going to rotate farther or faster. And the reason why is because linear speed, which we label as VT, a tangential speed, the linear speed, is equal to the angular speed times its distance. And so this distance term right here, R, is greater for ladybug A than for ladybug B. So linear speed will be greater for A than for B. And that's just another statement of fact. Linear speed is related to the distance from the axis. And because ladybug A is at a further distance than ladybug B, ladybug A will be moving faster. All right. Question B says, ladybug A begins walking in a circular path in the direction of the disk rotation. Does the magnitude of the angular momentum of the disk alone, not the system, but just the disk, increase, decrease, or stay the same? And so this helps to kind of see it as its own little diagram. And so anytime you see these problems like this where they're drawn at an angle like this, redraw it as kind of a overhead view. I think you'll be able to see it a little bit better. All right. So this thing's rotating counterclockwise. So this is the direction it's rotating. And ladybug A begins walking in a circular path around the circle in the same direction that it's traveling. So here's ladybug A right here. And it's going to start to rotate in the same direction, or walk in this same direction. So you can imagine you're on a merry-go-round or a carousel at the park, and you start walking forward, right? And so the question says, does the magnitude of the angular momentum, if you remember L, which is angular momentum, is I times omega, does that start to increase, decrease, or stay the same? For the disk, not for the ladybug, but for the disk. Well, I can't change the rotational inertia of the disk if I stay at the same distance away. because remember, rotational inertia is an mass times a radius squared term. And so that radius is staying the same, so you're not really changing this term. You're not changing the mass of the disk. You're not changing the size of the disk. So we can't do that. But what would happen to the angular speed? Well, if you start to walk forward, then that means you're exerting some kind of a force from your feet onto the bottom of the platform. And so you can imagine if I looked at kind of like a side view of the platform, and let's say that we're the ladybug, and we start to walk forward in this direction, that means right at our feet, we're exerting a force that goes backwards, right? So we're exerting a force onto the bottom of our feet, kind of pushing that platform backwards, right? And so as you're pushing that platform backwards, then that means that that platform will actually have a torque kind of internal to the system that pushes in the opposite direction that it's rotating. It's like, you're as you're walking, you can imagine pushing the thing backwards, right? And so what's going to happen is, yeah, that angular speed right here is going to decrease for the disk. Now, what does that mean in terms of you? Well, you're going to speed up, of course. Your angular speed is going to speed up. But for the disk, yeah, it slows down. And so that means that the angular momentum of the disk alone will decrease. Now, did it say, will the angular momentum of the system increase, decrease, stay the same? Well, the angular momentum of the system would stay the same. But for the disk, yeah, it goes down. All right. Question C. In a different scenario, a single ladybug is standing near the edge of the disk, 0.9 times the radius, and starts to walk towards the center. The rotational inertia of the ladybug disk system is I1, and the disk completes one rotation in 2.5 seconds. The ladybug then walks towards the center of the disk to 0.1, so it moves from here to here, so it's getting closer to the center, and comes to a stop relative to this. So the only thing that's happened is the bug walks towards the middle as it's rotating. Now the rotational inertia of the system is I2, and the disk completes one rotation every 2 seconds. So that means that the disk actually sped up. And we want to derive an equation for I2 in terms of I1. All right? So what I want to do here is write let me kind of sketch this out real quick. So initially the bug is at a distance of 0.9 times the radius. That's your initial rotation, or distance r. And then afterwards, the bug is 0.1 times the radius. Okay. So we want to see how this affects our results. All right. Well, these distance terms are actually irrelevant. All we really need to know is what their speeds are. So I'm going to set this up as a conservation of angular momentum problem. The initial momentum of the bug disk system will equal the final momentum of the bug disk system. L is just I times omega. And so we're going to have the initial, and I think they call that I1, okay, and the initial speed, omega 1. The final speed will be I2 times omega 2. All right. So what do we know about omega 1? Well, that's just a rotational speed. So that's number of rotations per unit of time. Okay. And in this question, it says it completes one rotation every 2.5 seconds initially. Now, it's not in radians. We don't really care about that. We just need to know that it has so many rotations every second. It would be 2 pi radians per 2.5 seconds. But we'll just leave it as a rotation. The final speed, omega 2, is 1 rotation every 2 seconds. And so now we have these two terms. It tells us what I1 is, it's just I1, and I2 is what we need to solve for. It says now the rotational inertia of the system is I2. To derive an equation for I2 in terms of I1. So in other words, I need to take this equation, solve for I2, which is going to be I1 times omega 1 divided by omega 2, which will just be I1 times 1 over 2.5 divided by 1 over 2.0. And when you get that calculation, it ends up being 0.8 times I1, or 4/5 of I1. All right. And then the last part of the question says, while the ladybug is walking toward the center of the disk, does it exert a torque on the disk? Well, here's the question. Did angular momentum change for the disk? Because the question says, while the ladybug is walking towards the center of the disk, does it, in other words, does the ladybug exert a torque on the disk? Well, did the disk change I? In other words, did the rotational inertia of the disk change? No, the rotational inertia of the system changed from I1 to I2. And so the answer to that question is no. And so then you need to ask, because the other term we need to know about is omega, did omega change for the disk? Well, yeah, it did. The speed went up. As the ladybug walked forward, the disk speed increased. So omega disk did increase. So therefore, what you can say is that, yes, the ladybug did exert a torque. You might want to put the word internally to the disk. This means the disk's speed increased. That indicates a change in angular momentum. And that's your solution for part C. All right, guys, I hope this helps. If you have any questions, please email me and be glad to help you out. Thanks a lot and have a good afternoon. Bye-bye.